Okay, so what I'm going to talk about is not so much about fundamental groups or periods, but more about Hodge classes or variations of Hodge structure. So then there's lots of people who know about these things here, obviously, and maybe others who don't know so much. But let me start by just saying sort of in a few sentences what the topic is before I give an actual introduction. So what I want to do is you have this this locus of Hodge classes. So this is a kind of situation where you have a family of smooth projective varieties, or you have a variation of Hodge structure. And then the locus of Hodge classes keeps track of all the Hodge classes in that setting, either in the fibers of the family or sort of abstractly in the variation of Hodge structure. And so what I want to do is I want to put this inside of a larger set that I will call the locus of limit Hodge classes. And here, this should take into account things that are not, that should also take into account things that are not Hodge classes, but classes that become Hodge classes sort of in the limit. And I'll make that precise later. So just so that you have one example that you can keep in mind of this kind of situation. So a typical example would be a vanishing cycle. So for example, you have some family of surfaces that are parameterized by a disk. So these are surfaces. And S0 has one ordinary double point. And so then in the nearby fibers, when T is small but not equal to 0, you have a two-sphere, which is the vanishing cycle. It's a two-sphere of, I think, self-intersection -2 or something. And this is the kind of class that becomes a Hodge class in the limit, which can have different meanings here. So in this specific geometric example, for instance, you can take a 2-to-1 covering of the disk and then put in a different fiber that is actually a smooth surface. And then in a very precise sense, that vanishing cycle so corresponds to an actual algebraic cycle, an actual P1 on that additional surface. Or you can think of, take the ordinary double point, blow it up, you get a P1, again self-intersection -2, and again that sort of corresponds to this vanishing cycle class. So I want to keep track of such kind of things. For the people who know about this, I should also say that it turns out that this is not really a new result. So what I'm going to talk about doesn't sort of involve any kind of new result. It turns out to be just a reinterpretation of the things that were done by Catani, Deligne, and Kaplan. So the whole thing I will talk about is actually just sort of an application of the main technical theorem that they prove, and maybe stating in a slightly different language. Okay. So yeah. So then let me actually sort of start talking about Hodge classes a bit. So I want to introduce a bit of notation, sort of review what the problem is, and I also want to say what this theorem by Catani, Deligne, and Kaplan is. So Hodge classes. So I will work with integral Hodge structure. So I will take H to be a polarized integral Hodge structure, where it could be of even weight, but I will normalize it to be of weight 0, so that I can keep the indices fixed. And so I will denote by Hz the underlying free Z module. And then I have the Hodge filtration on the corresponding vector space. So this is the Hodge filtration. And so to say it's a Hodge structure, of course, means that the vector space is decomposed as the subspace is HPQ, P plus Q equals 0, and HPQ is obtained by intersecting the subspace FP and the subspace FQ conjugate. And then the polarization will be, for reasons that will become clear, I will take it to be with rational coefficients. So I assume that the whole thing is defined over the integers, but the polarization not, because in geometric cases it won't be. Okay, so the polarization will be a form from HQ times HQ to Q. That gives the polarization. And one can summarize the conditions in the polarization by saying that this so-called Hodge, so you have this Hodge norm. So if I have a vector, then if you look at this particular form here, so you take I to the P minus Q, and then you look at the HPQs will always be the Hodge components with respect to this decomposition. Then this is positive definite. And I mean, for the corresponding inner product, this space is here is orthogonal decomposition, right? Those are the bilinear relations that go into saying it's a polarization. Okay, and so then a Hodge class is just, an integral Hodge class is just this space here. So you intersect the integral lattice with the space H0, which, because of the decomposition, is the same as intersecting it with F0. Okay, and so the basic fact, which is sort of important for everything here, is if I look at Hodge classes, then in this decomposition here, there's only a single term, namely the H00. And so for that reason, in fact, the value of the pairing and the value of the Hodge norm are actually the same, right? So if I have a Hodge class H, then the Hodge norm is, well, there's only one term, so this is just the same as Q of HH, and so this is greater or equal to 0, right? And so in particular, it means that if I look at those Hodge classes where I bound the size of this number here, so I'm going to call this number the self-intersection number. If I look at Hodge classes where I bound this self-intersection number, then there's only finitely many, right? So this says that if I look at, so I'll denote it like this. So this will be the space of H in such that Q of HH is bounded by K, then this is finite. Because it's the intersection of this ball with a discrete subset HC. Okay, so again, this I'm sure everyone knows, but so the typical example of this would be the cohomology of a smooth projective variety, right? So you could take H to be, say, take HZ to be H2k of x with coefficients in ck. So you put this k-twist to make the weight 0, and then you mod out by the torsion. Where x is smooth projective over C. And so this is the reason for allowing the polarization to be defined over Q, because of course in general you will take an ample line bundle, you have a Lefschetz decomposition, but that will give you a form that's only defined over Q. Okay. So if there's a question at some point, then please just ask, right? I will not just always. Okay, now we can do the same sort of thing in families, and then this is what the locus of Hodge classes is about. So for the locus of Hodge classes, so we look at so the setup is so I will have a complex manifold X. So I will state it in sort of complete generality. So I'll have a complex manifold X, which is embedded in some bigger complex manifold X. So this is a Zariski open subset in a complex manifold x bar. And then on this x, on x, you have a polarized variation of integral Hodge structure that I'll denote by curly h. So at every point of this x, you have a polarized integral Hodge structure of weight 0. And then I'll kind of use the same notation as up there. So the underlying, this will be the underlying local system. And then the vector bundle will just be noted by this curly h. Fp are the Hodge bundles. And then again, I have some polarization form. So I have some Q. OK, and so then in this setting, at every point of x, I have a Hodge structure, so I can look at all the Hodge classes over that point. And the locus of Hodge classes is just the union of all of these things together, basically. All the Hodge classes that occur in all the possible fibers of this. So let's see. So to define it a little bit more precisely, I need one bit of notation. So I have this local system here. And so now I'm going to do something that makes sense sort of only in a complex world, but not algebraically. Namely, I view this local system as being a complex manifold. So this HZ determines a complex manifold that I'll call TZ with a holomorphic map to X, which is actually just a covering space. So this is just a covering. It's like the total space of the sheaf or the sheaf space or whatever that's called. This is set up so that the holomorphic sections of this I exactly recover for you this sheaf, right? And so I think of the points of this as, so these are like pairs, like this, where X is a point in X, and then H is a class in the fiber of the local system. Okay, and so now the locus of Hodge classes, I can consider it as being actually a subset of this space, right? This TZ, the points of that tells me all the integral classes in my variation, and then I'll take so the locus of Hodge classes. So this is the set of points in here where H is Hodge. So in other words, well, it belongs to here, right? And then I also want it to be of type 0, 0. So like this. Okay, so this way I can write as a set. Of course, it has an analytic structure also, right? Because you see that inside of this complex manifold, I get it basically by intersecting with this holomorphic subbundle here. So in fact, I could also write this as this TZ intersected with this holomorphic. So I will write B of a sheaf for the actual bundle inside of okay, so since I'm assuming that things are torsion free, this local system here is a subsheaf of the vector bundle, and so that space TZ is a sub-manifold of the corresponding vector bundle, and then I'm just intersecting with the subbundle F0. Pardon? B it just means that, so the script H is a sheaf, and I just take the corresponding vector bundle, the corresponding holomorphic vector bundle. So it's sometimes called T of H or V of H or something. Okay, so this is an analytic Okay. So again, the typical example of this would be that you start with a situation where x and x bar are algebraic varieties, and then you have a family of algebraic varieties over x bar, where the fibers are smooth. A family of projective varieties parameterized by x bar, and x is the smooth locus of the family, so that the cohomology of the fibers gives you a variation of Hodge structure on x. No, so for certain reasons, I want to do it like in this sort of generality. Now, the main result about this locus of Hodge classes is this famous theorem by Catani, Dillon, and Kaplan, right? And so that exactly deals that the motivation for that was this algebraic situation. In the case when this data comes from a family of smooth projective varieties, then you have the Hodge conjecture, which tells you that these Hodge classes should, at least up to some multiple, actually correspond to algebraic cycles. And so the things that you're parameterizing here in this locus of Hodge classes actually should come from algebraic objects. And for these algebraic objects, you have moduli spaces. And so you'd expect that this has actually some algebraic structure. So in fact, in the case when H comes from a family of smooth projective varieties, over X, the Hodge conjecture predicts that Hodge conjecture implies that this locus of Hodge classes actually is, in quotes, a countable union of algebraic varieties. Okay, so is in the sense that there are these algebraic varieties, and if you take the corresponding analytic spaces, then you get this locus of Hodge classes. And so here again, the reason is the same as you usually have when you study algebraic cycles. So if the Hodge classes came from cycles, then you'd be looking at moduli of certain kind of cycles, and these would be parameterized by countably many algebraic varieties. So this is where the countable and algebraic come from. And the amazing thing is that even though we don't know the Hodge conjecture, this thing was in fact proved. So Catani, Dillon, and Kaplan in fact managed to show that this prediction is true, right? So this is, and in fact they prove a more precise statement, which I'm going to tell you now. So this is true by so I'd have to write this a lot, so I'll just, from now on, I just write CDK. In fact, they have a much more precise statement. So the more precise statement, I'll write as a theorem. So in fact, the algebraicity comes from a general property that this locus of Hodge classes has, even in the analytic setting. Namely, when you're in this kind of setup and you have X embedded in some bigger space, this locus of Hodge classes always behaves nicely at the boundary points. So in fact, so in the situation from above, so given as above, so not necessarily algebraic, but really a complex manifold and as a risky open subset, this locus of Hodge classes can always be extended over the boundary. So it can be extended to an analytic space that is finite over X bar. Finite, by which I mean proper with finite fibers. I put yeah, right. Yes. Yes, sorry. So I will, that's right. I will need to put here this bound on less or equal to k, right? So the point is that if I look at I can look at the corresponding set here, where I impose a bound on the self-intersection number, and then of course by this basic fact, the result will be finite over X, in the sense that, in the weak sense, it will have finite fibers over X. And this result by Katan-Dieling-Kaplan says that you can extend even over X bar and keep it with finite fibers and proper. Okay. And so in particular, as a consequence is in the algebraic setting, so when X is algebraic, but H is still an abstract variation of Hodge structure, then because something finite over something algebraic is again algebraic, you actually have a unique, so when X is algebraic, this has a unique algebraic structure. Right? Because by Gaga or something. Yeah. Huh? Well, no, it's finite. So you just take the push forward of the structure sheaf, and then it's a coherent sheaf, and then that's algebraic. Well, I mean, unique as in like compatible with the structure that is put on. Yeah, yeah, yeah. Yeah, right. I'm just talking about the. Right. I mean, so they give a kind of local construction of a space that extends it over the boundary, but they don't worry very much sort of about exactly what it is or what properties it has. Yeah. So in fact, so that's sort of exactly what I'm interested in. So, I mean, here you see that this theorem tells you that there is some extension, and I'm interested in the question of, is there some kind of canonical or nice way of extending it in such a way that the points that you add at the boundary are sort of geometrically meaningful. So that's, so maybe that's the goal. Okay, so find a sort of canonical extension where the points that you add over the boundary are geometrically meaningful. And well, so the answer will be this, or I mean not the answer, sorry. So one possible answer that I'm proposing is this locus of limit Hodge classes. So that I'll denote by something like this. And so as the name indicates, the point of this space will be something like limit Hodge classes, or to be more precise, equivalence classes of limit Hodge classes. Right. For the limit Hodge structure, you need. Yeah. I'll say something about that. I mean, this. Yeah. So let me write this here just once. So the points will be equivalence classes of limit. In quotes, limit Hodge classes. Okay. So whereby limit Hodge classes. Well, intuitively, I mean what I said earlier, namely classes that are integral and that are not Hodge, but that become Hodge classes in the limit, like a vanishing cycle. More specifically, it's going to mean something like Hodge classes in a limit Hodge structure, in a limit mixed Hodge structure. Yes.
But they will depend on the exact direction.
Yeah, that's right. So I will use all of them. That's right.
So it doesn't have to be Hodge for every direction.
No, I'm going to do it differently. So yeah, sorry. Then now I'm running ahead of myself. So right. So the situation will be this, that if I have like a curve in the base, then I'll have a limit mixed Hodge structure, which it depends on the choice of coordinates, of course. And I will look at Hodge classes in there, basically. And then in the end, I will use all possible things that I get in this way as the points. But then, of course, there's too many. So then there'll be some kind of equivalence relation that cuts it down to a reasonable size. Does that answer your?
Does not completely answer. Limit Hodge classes with respect to, that means there really is a chance of a bounded class of
Yeah. I'm going to define them right now. But yeah, sorry. Yeah, that's right. So right. Yeah. So I mean, I will. Yeah. So I will give an explicit construction of this thing, meaning I will describe it not just as a set or something, but I will give an explicit sort of analytic construction of it similar to this kind of construction here. Okay? And then, of course, you have to show that if you do some construction by intersecting certain things somewhere, that the points that you get really are interpreted as limit Hodge classes.
But my question is even more basic.
Oh, yeah.
Do they mean some kind of HC or non-boundable?
No, so where it will live is anytime I have a curve in the base, or like a little arc in the base that goes to the boundary at some point, I will have a limit mixed Hodge structure for that, and it will be Hodge class in there, basically. The collection of all of these things.
So your arc says that analytic disk refers to analytic.
Yeah, but I will take the so I will take the like finite monodromy subspace, so it will end up not depending on the parameter, actually. Yeah, right. There's many technical issues. It's sort of, for now, I'm just sort of saying vaguely.
But whatever it is, that guy's going to live over X bar.
That guy will live over X bar, yeah. And then, so we will, right, so now I'm giving away all the results at the very beginning. So of course, the analog of this theorem will be true, right? So the construction will have the property that the space that you build, it will be something that's finite over X bar. Yeah, okay, so now you can go home because you already know everything. All right, so then let me talk a bit about limit Hodge classes. Okay, so this should at least answer that question more precisely. So the first case to consider is just a case over a punctured disk. So let's look at the case where I have a punctured disk of some radius. So I have a little disk, and then I look at the complement of the origin. So punctured disk. And then I have some h on delta star. So integral derivation of Hodge structure, weight 0. So then this h, it has the monodromy transformation that I'll write as t, corresponding to some choice of generator in here. And because I'm working with things that are defined over the integers, it's quasi-unipotent. So I can write it as some semi-simple part times some unipotent part, where this has finite order, and this n is nilpotent. And so this, having this by the paper of Schmidt, it determines a limit mixed Hodge structure. So this determines, not quite uniquely, a so-called limit mixed Hodge structure. So a weight filtration and a Hodge filtration on the, say, on the general fiber of this, on the generic fiber. So yeah, there's a, right. So right. Yeah, this thing depends on coordinates. So the way you get this is, so this W is the filtration, the increasing filtration determined by this nilpotent operator n. So this is the so-called monodromy filtration. So it has the property that n lowers the weight by 2, and it satisfies the Height-Lefschetz theorem, right? So graded quotient in degree k is isomorphic to the graded quotient in degree minus k by, and the isomorphism is given by n to the k. And then this f is something that's constructed out of the variation. So this is the limit Hodge filtration constructed by Schmidt. And this actually depends on the choice of coordinates. So if you choose other coordinates, then you end up replacing this filtration by some filtration that looks like this for some complex number. Okay, so depending on, I think, the first derivative of the coordinate or something, this filtration can change. But inside of, and okay, then Schmidt proved that, so this is a mixed Hodge structure on this vector space. So on each graded quotient, you have something pure, and you know very precisely the behavior of this bilinear pairing that gives the polarization. Like, you know where it's positive definite and where it's negative definite and things like that on the graded quotients. Okay, so now this n is a minus one morphism of this mixed Hodge structure. And so if I look at the kernel of n, then this is actually a submixed Hodge structure, which is now independent of the choice of coordinates. Of the coordinates. Right, and of course, because of how T looks like, the points of this kernel of n are exactly those classes that have finite order monodromy, and have finite orbit under applying T. And so a limit Hodge class will be a class in there. It depends on. Yeah. So right. So it depends on how you do it exactly. I mean, so if you fix the fiber like this, then you have this dependence on this point little x, but that's sort of choosing different points will be absorbed into this kind of thing here. Alternatively, you can say that this HZ is that you pull it back to the universal covering space and take the global sections there, and that's fixed, but then again the embedding of HZ into the vector space ends up depending on the choice of coordinates exactly. Okay, but in any case, if I look at the kernel of n, then that is well-defined independently of the coordinates. And so limit Hodge classes will be classes in there, basically. So this will be the kernel of n in here, right? So, so i.e., these are usual Hodge classes in this mixed Hodge structure, WF. So, i.e. a morphism from Z of 0 into this mixed Hodge structure, but with the additional property that they have finite order monodromy. So with finite orbit under T. Okay, and so again, let me point out why I'm looking at these particular classes. So the reason is that in the case when your variation on the puncture disk comes from a family, and when you have a central fiber to be filled in, that these are the classes that are sort of geometrically meaningful in terms of the central fiber. So if you have so this is the content of this Clemens-Schmidt sequence of the local monodromy theorem. So if you have a situation where you have some family of varieties over delta, where this xt is smooth projective, so projective and smooth, if t not equal to 0 and say normal crossing at 0, say reduced, let's get into the most standard situation. then you have this invariant cycle theorem. I mean, local, that says that at least I think over Q, the cohomology of the central fiber surjects onto the kernel of N. So any class in here can actually be lifted to a Hodge class on the central fiber. And so these things are things that really come from yes, that's right. Yeah, so I will, right, maybe I'll try to say something about that later. So what actually happens here? So I mean, so one of the results that Schmidt shows is that not only is the N a morphism, but the S actually is also a morphism of the variation Hodge structure. It preserves both the W filtration and the F filtration. And so it means if I have one of these, then the whole orbit under T, which is the same as the orbit under S, actually also consists of Hodge classes in this sense, right? And geometrically, like in terms of this covering space picture that I was drawing earlier, what this looks like is that I have the disk downstairs, and the classes together will also form a disk upstairs. Sorry, this covering space TZ that I was, so here this TZ over the style that I was drawing earlier. If I have a class that has finite order under monodromy, then I'll have this puncture disk downstairs, and the classes upstairs with that property, they will form another copy of delta star, but that projects down to this copy of delta star by something like T goes to T to the K. Right? And so also in terms of building extensions or something, that's a very natural situation to consider, because you see that then here I have delta star mapping to delta star by T goes to T to the K. There's an obvious way to fill that into a finite map, right? Just fill in to the disk and the disk downstairs and keep the map T goes to T to the K. So that's sort of what you would do in this kind of case. All right. So that's the case over a disk. Now in general, so I will just consider arcs. So I consider holomorphic arcs from, again, a little disk into X bar with so the puncture disk gets mapped into the open set, and the origin gets mapped into the boundary. And so then I have this VHS that I'll call F inverse H on delta star by just pulling it back from X. And so I have limit Hodge classes for that in that sense. And so a limit Hodge class for this variation on this X bar is just going to be one of these sort of things. Okay, so a limit is any limit Hodge class for on delta for any such F. Okay, so just look at all possible Hodge classes that you get by looking at all possible limit mixed structures for these kind of curves. So there's of course going to be a very big number of them, but we'll take them out to some kind of equivalence relation to make something finite. But I want to emphasize again that these classes are geometrically meaningful. So if I'm in a situation where I start from a family of projective varieties over X bar, and X is the smooth locus, then of course anytime I have such a curve, I can pull the whole family back to get a family over delta. and I can perform semi-stable reduction to get into this kind of normal crossing setting here. And so then I know that these limit Hodge classes actually come from Hodge classes on like normal crossing varieties. It's just that in order to find the variety, you'd have to do semi-stable reduction and so on. Right? But this is some of the Hodge theory analog of performing that kind of operation. Okay, and so then let me, yeah. Yeah, so for now I've just described them as a set, right?
Where do they live in kind of like the genetic fiber?
Where
In the terminal sense, but I mean, that depends on the check.
yeah, so I mean, so they still sort of live, I mean, if I have some particular boundary point, and I'm talking about limit Hodge classes at that boundary point, they live in, for example, some choice of nearby smooth fiber, right? But I mean, it would sort of depend on the exact choice you make.
The way I think of it, I prefer to believe that you take the fiber of the canonical extension
Uh-huh.
as the vector space where you do it in the kernel or end.
Yeah, you could do that, right. You could do that too. No, so I want to take it arbitrary because, yeah, right. Yeah, so to answer your question, so what we'll do is, I mean, I haven't stated the result yet, but so the actual sort of analytic construction of the space will go, you go to the normal crossing situation, and there you can write things down in terms of the canonical extension. And so there things will actually live inside the canonical extension. And then you have to find some construction to descend it to this. Yeah. Okay, so let me state the result first. So as I said, this is basically a corollary of the Kaplan paper. So so I will denote the set of all of these. Well, no, I won't. So there is a, I mean, in the same situation as above. So given x contained in x bar and script h, there's an analytic space. That I'll denote like this. So here you indicate the larger manifold with a holomorphic mapping to x bar, such that, so first, so over x, it's just the usual. You get just the usual locus of Hodge classes. So we're only adding points over the boundary. And then secondly, the points. I will get to that in a moment. Yeah. So I'm sort of stating it for the union over all of ones that where you put a bound on the norm. So the points of this space are in bijection with equivalence classes of limit Hodge classes. And then lastly, so you have some notion of self-intersection number still because you still have this pairing. So this space is the union of all the ones where you bound the where you also put a bound on the self-intersection number, right? In the obvious way that you're still just asking, here you're just asking for classes that where Q of HH is bounded by K. And then the main result is sort of that these are all finite over X bar. These individual components where you put the bound. Where do they live? Yeah, so right, there is. So right, so I will construct, I will give a sketch of how you construct it. So where it will live is in the case when x in X bar is like the complement of a normal crossing divisor, this thing will live inside the canonical extension. of the underlying vector bundle. I should have, yeah. So you're asking the questions always in wrong. Okay, so maybe I'll. Okay. So let me write this down here. So, yeah. No, so I mean in that case, by what I said here, these limit Hodge classes would be certain Hodge classes on the central fiber. But I mean modulo the morphism in the Clemens-Schmidt sequence, right? So I'm only looking at sort of the image inside of the limit mixed Hodge structure.
Suppose you blow up and see different guys with going across the situation.
Yeah.
Apply the theorem up there and you
Yeah.
get some
Yeah.
Hodge classes
Yeah.
up there. What's the relation of that to the Hodge classes?
Yeah, I was about to write. I'm going to write this down now. So right. So here's the idea of the construction. Sort of briefly. So the first part is you do the case where it's a normal crossing divisor and H has unipotent monodromy, local monodromy. And then the second case is sort of the general case. So maybe, yeah. So maybe, again, because everyone seems to want to know it earlier than I was going to say. So in the normal crossing case, here's what you do, right? So I'll just, for those who know, I will just say sort of what it is now. So the way this will be defined is, I use this notation to denote the canonical extension. Of the underlying flat bundle. And then it's another theorem by Schmidt that the Hodge filtration actually extends to a filtration by subbundles. So this is a holomorphic subbundle extending. And so then we're going to do something similar to the definition of the locus of Hodge classes itself. So I'm going to, inside of this vector bundle corresponding to script H, I'm going to take a certain intersection. So what I'll do is I have this space TZ, which is embedded in the bundle script, in the bundle H. I view it as a submanifold of this bigger vector bundle over X bar, this bundle of X tilde. Then this is no longer closed, of course. I take the closure and show that that has sort of nice properties. Yeah, so this is the manifold corresponding to the local system. Yeah, sorry. So it's the intersection with this Hodge bundle. Yeah, sorry. So sorry. So this means take the closure of this TZ inside the bundle, the canonical extension bundle, which contains the original bundle as a dense open subset, right? So this TZ was a closed submanifold of here, but it's no longer closed in this bigger bundle. I just close it up, show that you get something nice, and then you can intersect it with this subbundle to get an analytic subspace of this bundle. And then I claim that that has the right. One can deduce from Katanidli and Kaplan that that has the right properties. Okay, so like, let me write this down. So this involves two claims. That the sort of very easy one is that this closure is analytic. So this is easy. And then the second part is that the intersection. So if I also look at the bounded self-intersection number one, and I put this bound. So this is just the this has a certain number of components on each of which the self-intersection number is constant. I just look at all those components where the self-intersection number is at most k. And I look at the stuff that I get, and that this is finite over x bar. And so this follows from the more technical parts in CDK. Okay, and then, so this is how to do the normal crossing case. And then for the general case, so you first take a resolution, so take a log resolution. Which is an isomorphism over X. So then if I do this, it will make the local monodromy quasi-unipotent, but not necessarily unipotent. So then so locally on X bar prime, it's going to look like I'll have a polydisk, and so say with some coordinates t1 up to tn, and this is say the divisor given by, I mean the reduced divisor given by this, right? Said theoretically. And the monodromy is, so the monodromy is quasi-unipotent. So if you know the first part, you know how to deal with the unipotent monodromy. So first you have to go to the case of quasi-unipotent monodromy. So you take a finite cover that in the first so many variables, you take a finite covering to make the monodromy unipotent, to get. And so then by 1, if you grant yourself 1, then you know that you have this space Hodge, say let's say equal to k, of script h on, let's call this p, on delta to the n. On this particular copy of, let's call this with S and with T. Okay. Now here, since everything is pulled back, and since this space comes with this obvious action by finite group, this finite group is going to act on this guy. And by finiteness and properness, I know that there's a quotient, so I can take a quotient. So then I will take. So take. Okay, and then the last question is sort of, now I get you show that they can be patched together on overlap so that you get something that lives on here. And then the last question is, how do you descend it back down to here? And so then the observation is that this mapping, if I get it, for example, by blowing up, this is going to be something proper, but it may have fibers of positive dimension, right? What I want is something that's finite over the base. So I'll be forced to contract all these positive dimensional fibers. And again, because everything is proper, I know I can do that by just taking sign factorization. So then what you do is you descend to x bar by sign factorization. So in other words, you have which is finite. You have this mapping here, which is proper. and which I can arrange to have connected fibers. And then, since I want something finite over here, I just take the Stein factorization. And then this will make this guy finite, and that will make this one here proper with finite, with connected fibers. Okay, so this thing here will be the Stein factorization. Of the
I mean, upstairs is a Hodge the only definition of this
yes, yes, yes,
Now it depends
yes. Yeah. Yes, right. But so it's just sort of the description that comes out of this, right? And remember, I said earlier that we're not going to take all the set of all possible limit Hodge classes anyway, because that's a much too big set. And because, I mean, surely I can have a curve that comes in, and I can have another curve that comes in very tangent to it, but it's technically a different curve, then there would be different limit Hodge classes. But I want to be able to identify such things. And this is the same kind of thing that will happen here. So here, the points upstairs are limit Hodge classes. And when I take the Stein factorization, I still get limit Hodge classes, but now up to some bigger equivalence relation. And the bigger, since the fibers here are connected, the equivalence relation will be something like, if I have one limit Hodge class, another limit Hodge class, if I can connect them by a holomorphic family, they'll become equivalent. Right? So if I have this one curve here and a limit Hodge class on it, I have this other curve and a limit Hodge class on it. If I can sort of move it holomorphically from one to the other, maybe in several steps, then they will be considered equivalent. And so by that, I take out sort of all the continuous part in these limit Hodge classes, and I leave only sort of the discrete invariance after that, right? That will be the effect of that. Yeah, I think so. Although I have to admit that I haven't sort of carefully written down its invariant of the construction part. But I think so, because I mean, again, you can choose sort of common resolutions that dominate both, and you can make comparisons between these spaces. And I mean, it will be possible to describe this also by some kind of, you will be able to characterize this sort of uniquely by some kind of lifting property of what happens along curves, right? And you will be able to say that if you have a curve down here with corresponding to some limit Hodge class, it's going to lift uniquely into a curve in this space. Things like that. So you could also give them sort of invariant description like that.
But I mean, for algebraic sequential, you don't need to go to X bar general, what you
Yeah.
get about this.
Yeah, that's right. Okay, so now of course there's not much time. Okay, so I'm afraid I will have to, for this part, I won't be able to say anything. So yeah, so the question is, why do I care about the case of an arbitrary compactification? So, for example, in the Khatani-Deligne-Kaplan paper, if you, to just prove analyticity, prove algebraicity or something, it's of course enough to get it algebraic over some model. So you don't have to worry about this descending part. But I'm interested in situations where either the geometry of this X bar, of a specific X bar, is very nice. So for example, family of hypersurfaces in projective space, or family of hyperplane sections of some given variety. In that case, this X bar would just be a projective space, so it's very nice, but the complement divisor would be very complicated. And then I don't know explicitly how to resolve it, and I don't know how to do anything. So it's for those kind of cases. Also, I'm hoping that this can be used to some extent for certain numerical constructions. So, I mean, you have cases where, sort of based on dimension counting, each component of this locus of Hodge classes has expected dimension 0. And then I would want to sort of associate some numbers to these components. And I want to do that in such a way that it sort of extends to this locus of limit Hodge classes. And so again, I don't want to sort of arbitrarily modify the base, because it may be that the base that's given to me at the beginning is the one in which it has very simple cohomology or something like that. So I want to be able to find these numerical invariants in that particular model and not have to go to some resolution of singularities and introduce additional cohomology and so on. So that's why. Yeah. Okay, so then, sorry, so I just say one word about this, so not even writing anything. So here, as I said, that it comes into these two parts. So you first have to prove that this closure is analytic. That you need just to get the analytic structure on the space, right? Because I want to. If you write it out in local coordinates, it's just a simple sort of linear algebra problem. I mean, in local coordinates, in the normal crossing case, you have an explicit model for how this embedding of the local system into the vector bundle looks like. And then you just need to just calculate what all the possible limit points are and just find some equations and so on. So it's just a linear algebra kind of question. This part here, again, over the part that lies over X, it follows from Katanidin-Kaplan, right? I mean, every component that actually has some part lying over X, Katanidin-Kaplan will tell you it extends finitely and properly. So the question is just, what about the stuff that lives entirely over the boundary? And so it turns out that if you have a limit Hodge class, it will of course not come from actual Hodge classes in your actual variation. But if you're willing to replace your variation by some other variation, it will come from Hodge classes. So what you do is you replace your variation by a certain approximating variations of Hodge structure called nilpotent orbits, and you apply the Katanidin-Kaplan to these nilpotent Katanidin-Kaplan theorem to these nilpotent orbits. The limit Hodge classes come from actual Hodge classes in these nilpotent orbits, and so the Katanidin-Kaplan theorem sort of controls their asymptotic behavior. And it turns out that if you do it nicely, it sort of controls it enough to prove all the properties that you want to prove. So the finiteness and also the properness.
So there are some components of this guy that just completely
Yeah, this will have, for example, like I said earlier, for these families of surfaces, the vanishing cycle, they will be a component that lives entirely over the boundary that you don't see over the smooth locus.